Hi everyone. This lesson 1.4, is looking at the same future value and present value formulas, but instead of trying to find a future value or a present value, we're going to try and solve directly for n, the total number of compounding periods, and I, which is the periodic interest rate. So in order to do that, we'll start with finding n. To find n, I'm going to walk you through the steps to figure out that formula. I don't expect you to know how to do these steps. I just want you to be able to understand it. It just helps you when you're looking at formulas in later questions that we're going to do in these problems. But starting with finding n, we're going to have to use a natural logarithm. So you all remember the ln button. It says ln on your calculator. That's going to become really important when I show you how to derive this formula. So if you remember the ln button, when we learned this, we had two different exercises. We had log and we had ln. Okay, so log on your calculator was always to the base 10. The ln button was always to the base of e. Remember, e is an irrational number that has a never-ending amount of decimal places. And if you were to put e on your calculator, it's 2.718281828. With multiple decimals, it never fully repeats itself. The important thing is not knowing that number, but just knowing how to use that button on your calculator and knowing the relationships between different ln functions. So this was back to the first course, our course last term, and there were three really important rules. The first one was if you had two items, okay, that were a product of each other, an example could be ln of 3 times 2. That was the same as ln 3 plus ln 2. In other words, putting ln 3 in your calculator, pressing enter, plus ln 2, and putting that in your calculator, pressing enter, and adding those two together. Now, if the two numbers are being divided by each other, okay, so using the same example, we'd have ln of 3 divided by 2 instead of multiplying. That was the same as ln 3 minus ln 2. Now the third example, and this one is the most important one because you're going to see how this relates to our future value formula that we're going to look at. So the ln, okay, of any number to the exponent of something, so again using our same values, we could say ln of 3 squared is the same as taking that exponent and multiplying that ln term by it. So in other words, it becomes 2 multiplied by ln 3. Okay, so you're basically taking that exponent and moving it down behind the term. Okay, so that's useful because it lets you now have this value that's in the exponent within the equation for you to solve using algebra. So using adding and subtracting to both sides, or multiplying and dividing to both sides. So let's look at how this formula is derived. I've listed all the steps. It's over two different slides. Again, I want you to know the end formula. Okay, like I'm not going to expect you to have that formula memorized, but I do want you to follow along with how I've derived this. It just gives you a better understanding kind of how these formulas work. So I'm going to start with the future value formula. So the future value is equal to the present value times 1 plus the periodic interest rate, and that's to the exponent n. So you see, we're trying to solve for this exponent. So that ln rule that said ln of something to the exponent k, we'll call it a to the exponent k, was equal to k, or in other words, that exponent times ln of a. Okay, so that's important now, right? Because now that exponent is just sitting there being multiplied by that term, so we can solve for it on its own, right? And if it's in this form, a to the k, you can solve for that term, but you're not solving for that term k by itself. So going back to our formula, we've got the future value is equal to the present value times 1 plus the periodic interest rate to the exponent n. So now we're trying to get n by itself. So my first step is I have present value here on the right-hand side being multiplied by this big term, ln, or 1 plus I to the exponent n. So I'm going to first remove that from the right side of the equation, because again, on this right side, I want to have just the value of n. So to do that, I'm going to divide both sides of the equation by the present value. Okay, so I've divided both sides by PV. And now on the left side, it's future value divided by present value. And on the right side, these present value terms would cancel. Okay, and they just become 1. So what you're left with is your future value divided by your present value is equal to 1 plus I to the exponent n. Now, remember, going back to this ln that I showed you, this ln rule, remember the rules still apply that if you do some kind of mathematical expression to one side of the equation, you have to do it to the other side of the equation. So you can see I've got this term here, 1 plus I to the exponent n. So it's a perfect candidate to use this ln rule on. But if you do that, you have to take the ln of both sides. So what you do to one side of the equation, you have to do to the other. So I'm going to take the ln function of both sides. So the left side becomes ln of the future value divided by the present value. And the right side becomes the ln of this entire term, 1 plus I all to the exponent n. Okay? So now that we have that, remember our rules. Okay, so in this instance, we had ln 1 plus I to the exponent n. Remember, our rule was you could take that exponent and move it down behind that term. So that became n times ln 1 plus I. So I've substituted that into this equation here. Okay, so I've basically used that rule. The left-hand side, there wasn't any rule we could do. You could technically do the rule where you could do the ln of the future value minus the ln of the present value, but we're not going to. We don't really need to in this equation. Because we're solving for n, at the end we're going to know all these variables. We need to know the future value, the present value, and the periodic interest rate, or we can't solve for n, right? Because we don't have enough information. So now we have n just sitting here on the right hand side, not in an exponent. So now we need to solve for n. So in order to do that, okay, n is being multiplied by ln 1 plus I. So just like any other term, I can just divide both sides by ln 1 plus I. There's no reason why I can't, because if the same term is in the numerator as the denominator, it cancels. So this ln 1 plus I cancels on the numerator and the denominator. So we're left with, okay, just rearranging this, n, okay, is equal to the ln of the future value divided by the present value divided by the ln of 1 plus I. So this formula seems, very complicated, but if you follow those steps to how I derived it, you'll see that this gives you an easy way to just plug those numbers now into your calculator to solve. One item you do have to keep in mind, okay, we're solving for n, and remember n is the total number of compounding periods, which is equal to the number of years multiplied by the number of compounding periods per year. So you'll see in our questions that once you solve for n, usually you're going to have to convert it to a certain number of days or a certain number of months, okay? So let's look at an example. In how many years will $2,000 grow to $2,440.38 at 4% per annum compounded quarterly? Okay, so a couple things, okay? This is actually after finding n, so disregard that it says I here. So we know we're solving for n, so I'm going to start by just writing the formula. N is equal to the ln of the future value divided by the present value divided by ln of 1 plus our periodic interest rate. So there's 3 terms that we need to know in this expression: the future value, the present value, and the periodic interest rate. So I'm going to start by writing our present value, because it's in the question, of $2,000. Our future value is $2,440, $2,440 and 38 cents. We know our nominal interest rate is 4%, which is equal to 4 divided by 100, removing the percentage sign, which is equal to 0.04. The other item we know is the number of compounding periods per year, m. It's given in the question as quarterly, so it means that m is 4. So now we can calculate the periodic interest rate, I, which is equal to j divided by m, and that is 0.04 divided by 4, which is 0.01. So we have everything now to just substitute into this equation, okay? So now you're going to see, well, we had to do a lot of math in order to derive this equation. Now that we have it, we can just substitute these values in. So all these items we did on the right-hand side here were the same that we've done in every other question, okay? It's just a different formula that we're substituting the values into. So if I substitute those in, I get that n is equal to the ln of the future value, $2,440.38, divided by the present value, $2,000. And that is divided by the ln of 1 plus 0.01. Okay? So when you're doing these, placing these in your calculator, all right, you press ln for some of you, and then I like to put brackets if I've got multiple items. So a bracket, $2,440.38 divided by 2,000. Okay, end bracket. That gives you the ln for the term in the numerator. Then you divide that by, you do the same thing. The denominator is the ln of 1 plus 0.01, which is 1.01. And you get a number, okay, when you divide that out, of n equals 20. Remember, that means that there's 20 compounding periods total. Our question asks in how many years. So we know, remember, that n is equal to the number of years multiplied by the number of compounding periods per year. So we can substitute these values in. N is 20, and that equals the number of years, we don't know that answer, multiplied by the number of compounding periods per year, which is 4. So now we need to solve just for this number of years. So to do that, we have to remove the 4 from the right-hand side. And we do that by dividing both sides by 4, right? So that means 4 divided by 4 cancels. And we're left with our number of years is equal to just 20 divided by 4. Or in other words, 5 is equal to the number of years. That means it would take 5 years for this investment to grow from $2,000 to $2,440.38. Okay? So let's look at another example. How long does it take for $400 to double? In other words, go from $400 to $800 at 5% compounded annually and at 10% compounded annually. So remember our formula, n is equal to the ln of the future value divided by the present value, divided by the ln of 1 plus the periodic interest rate. So we know in this question that the future value is $800, or in other words, double what you started with, because the present value is $400. Now, we need to solve for the periodic interest rate. So we know in part A, call this part A, that your interest rate is 5%, which is equal to 5 divided by 100, removing the percentage sign, which is 0.05. M in this case is simple, it's just 1, right, because it's compounded annually, and that's the case for both parts A and B. So your periodic interest rate I is equal to J divided by M, which is 0.05 divided by 1, or just 0.05. So that's for part A. So we can substitute those values in. N is equal to the ln of 800 divided by 400 divided by the ln of 1 plus 0.05. And if we calculate that out, we get a value of n of 14.2. So again, we have to make sure that we've converted that to years. So that is actually equal to the number of years multiplied by the number of compounding periods per year, m. in this case, m is just 1, right? So that means that 14.2 is equal to the number of years multiplied by 1. So that means that the number we received is just the answer. So that means the number of years is 14.2, right? Now looking at part B, all right, we have the same future value and present value, $800 and $400. And our interest rate is the only thing really that's changed. It's 10%, which is 10 divided by 100, removing the percentage sign, which gives us an answer of 0.10. Now, our number of compounding periods, again, it's annually, so m is 1. So we can solve for the periodic interest rate I, and that's equal to j divided by m, which is 0.10 divided by 1, or I is just equal to 0.10. So now again, for part B, we can substitute these values in. I'm sorry, I'm running out of space on this slide, but you can kind of see we're going to use the same formula. All right, I'll do it in a different color that we started with. So n is equal to the ln of 800 divided by 400, and that's divided by the ln of 1 plus 0.10. And if you calculate that out, you get 7.27. And again, because it's compounded annually, right, that means that m is 1, just like it was in the other question. So that means this value is actually the number of years, right? Because you're compounding annually, you're only compounding once per year. So for part B at 10%, it would take you 7.27 years in order to double your money. So let's look at a third example before I go into something a little bit different. It's going to require you to do a little bit more thinking on the original formula that we had. So how many years will it take for $5,000 invested at 6% compounded monthly to grow to $15,000? So I'd like to start with our formula. N is equal to the ln, the future value divided by the present value, divided by the ln of 1 plus I. Okay? The reason we know this is the formula is because it's asking for how many years it will take in the question. Okay? It's not asking for a present value or a future value, or you'll see later in this lecture when you're asking for the actual interest rate. Okay? It's asking for the number of years, which you would find by calculating n. Okay? So that's how you can distinguish which type of question this is. So we know a couple things. The future value in the question was $15,000. The present value was $5,000. Our nominal interest rate, J, is 6%, which is equal to 6 divided by 100, removing the percentage sign, which is 0.06. M, again, provided in the question, is monthly, which means the value is 12. So our periodic interest rate I is equal to J divided by M, which is 0.06 divided by 12, which gives you 0.005. So now we have all the information. We simply just have to substitute it into this equation. N is equal to the ln of 15,000 divided by 5,000, divided by the ln of 1 plus 0.005. Okay, if you calculate that value out, okay, remember ln 15,000 divided by 5,000, and that's divided by the ln of 1.005. You get a value for n of 220.27. So remember, that's the total number of compounding periods. Okay, so we need to figure out how many years that is. Remember the formula for n is equal to the number of years multiplied by the number of compounding periods per year. So we know n is 220.27, and that's equal to the number of years, which is the value we don't know. Remember, in the question, it's asking for the number of years. And that's multiplied by the number of compounding periods per year, which was monthly, so it's 12. So now to solve for the number of years, we need to remove this 12 from the right-hand side of the equation. So you divide both sides by 12. So the 12s cancel on the right-hand side. And we're left with 220.27 divided by 12, which is 18.36. And that's equal to the number of years. So in other words, it'll take just over 18 years for a $5,000 investment to grow to $15,000, given this interest rate. Okay? So we're going to look at a little bit different example for this fourth one. Okay? A loan of $2,000 taken out today is to be repaid by a payment of $1,200 in 6 months and a final payment of $1,000. If interest is 12% compounded monthly, when should the final payment be made? And I'm asking for your final payment number in days. So you'll read this question and it looks, like you're trying to do something from our last lecture, which is figuring out equivalent payments or what your payment should be. But the payments were provided in this question. What it is asking you for is when. All right, so there's two steps to approaching this problem. The first step is doing just what we did in the past with equivalent values. All right, so you start with a graph, and you know that in today, the loan is worth $2,000, and you're making two payments. You're making one in 6 months, okay, so we'll call it 6 months, for $1,200, and you're making another one. Okay, at the end, you don't know when it is, but you know that it's $1,000. Okay, so these are at different periods in time. So our first step is we have to place them at the same time period. So I'm going to place them all in today's time period. Okay, so in other words, our focal date will be today. All right, so we can start with a formula here. Okay, so we know that $2,000, that's today's value, has to be equal to the present value for item number 1. Okay, we'll call this one number 1, plus the present value for payment number 2. Okay? The thing is once we start substituting values in here, okay, so we have $2,000, that's equal to the future value of payment 1 divided by 1 plus the periodic interest rate. And I'm going to say the number of compounding periods is N1, plus the future value of payment 2 divided by 1 plus periodic interest rate, exponent N2. So you'll see that we've got two present value calculations here, all right? And I'm going to just start calculating numbers, and we'll substitute them in, and we'll see how the numbers progress. So let's look at our first couple items. Okay, we know our future value of payment 1, that's the number that you're going to pay in 6 months, which is $1,200. We know the future value for payment 2 is $1,000. That's how much you're going to pay. You just don't know when. For the question, it only gave you one interest rate and compounded monthly. So the periodic interest rate and the number of compounding periods per year would be the same for both payments. So your nominal interest rate is 12%, which is equal to 12 divided by 100, removing the percentage sign, or 0.12. Your number of compounding periods, it's given as monthly, so that means M is 12. So you can calculate your periodic interest rate, which is I, which is J divided by M, or 0.12 divided by 12, which gives you 0.01. So the item that you do know, okay, you can calculate the number of compounding periods for the first payment because it was 6 months from now. So N1 is equal to the number of years multiplied by the number of compounding periods per year. So you know it was 6 months. And remember, you have to convert months to years. So 6 divided by 12, since there's 12 months in a year, that'll give you 0.5. Or you can leave it as 6 divided by 12. So N1 is equal to 0.5 times 12, the number of compounding periods per year, or 6. Now N2, you don't know the number of compounding periods for the second payment because that's the item you have to find out. All right? So I'm going to substitute all these values in. You end up with $2,000, and that's equal to the future value 1, $1,200, divided by 1 plus 0.01 to the exponent 6, plus future value 2, 1,000, divided by 1 plus 0.01 to the exponent n2, because you don't know it. So now you can simplify a little bit, right? So you can do 1,200 divided by 1.01 to the exponent 6, okay? And if you substitute those values in, you get that 2,000 is equal to $1,130.45 plus 1,000 divided by 1 plus 0.01, and that's to the exponent n2. So I'm going to simplify this, all right, because we can take this $1,130.45 and we can remove it from the right side by subtracting it from both sides. I'm sorry, I ran out of room. And if we do that, okay, moving back to here, we get $869.55 equals 1,000 divided by 1 plus 0.01 to the exponent n2. Now, what do you notice about this final equation? All right, one thing to notice here is the only unknown now is n. We know the periodic interest rate, we know the future value of this payment, and we know the present value. That's how much is left in today's dollars after we've removed this first payment that we've made. In other words, this value is the present value of that payment. That's how much is left to be paid on the loan at that period in time. Okay, after this $1,000 was discounted all the way back to here. Okay, so that's the key thinking you had to figure out here. All right, so that means that we have a present value, a future value, and a periodic interest rate. So we can use the formula that we've derived, which is n is equal to the ln of the future value over the present value divided by ln of 1 plus the periodic interest rate. So we can substitute these values in. That's equal to the ln of 1,000 divided by $869.55 divided by the ln of 1 plus 0.01. Okay? If you calculate that out, all right, ln 1,000 divided by 869.55 and divided by ln 1.01, okay, you get a value of 14.04. And you know that that has to be equal to the number of years multiplied by the number of compounding periods per year, which is 12. So we can solve for the number of years. All right, sorry, I'm running out of space. So you can solve for that by dividing both sides by 12 in order to solve for the number of years. So you get that n, okay, the total number of years, is equal to 1.17, and you could multiply that by 365 days in the year, because remember, our answer has to be in days, and you get 427 days. Okay, so there were a lot of steps in that problem, but basically what we got to was that we got to a formula that was actually the present value of that last payment. So we were able to then use this formula for n that we derived earlier in this lecture. If that piece was confusing to you, I encourage you to pause, go back, and start at this slide again. Just watch it a second time. It's a new concept that we haven't yet kind of looked at, where you have to figure out, oh, that's actually a formula that I know, okay? So look at this question again if it's confusing. I'm also going to do one more example that's a little bit more in depth on the next slide. Like I said, let's look at one more example. An existing financial agreement requires 3 payments, $2,000 in 6 months, $3,000 in 15 months, and $5,000 in 24 months. Alternatively, a single payment equal to the sum of the required payments, in other words, $10,000, which is 5,000 plus 3,000 plus 2,000, could be made. If money is worth 9% per annum compounded monthly, when would the single payment have to be made? So just like the last question, there's 2 steps to this problem. First of all, you see that there's multiple payments, right? And you see that you're trying to make a single payment instead. So your first step has to be starting with a graph, okay? The second step is because the question asks for when. So you know you're going to get to a point where you end up with a future value or present value equation that you then can use our new equation to solve for n that has ln. So this is going to be today. And let's first look at the payments. First payment, 6 months from now, is $2,000. Your second payment, 15 months from now, is $5,000. And your third payment, okay, is 24 months from now. I'll put it at the end, and it's $5,000. So somewhere in here, your second payment was $3,000. Had that mistaken. So somewhere in this time frame, you have to make a payment. I'm just going to place it here. You don't know when it is. Okay, I'm just going to place it there. But you do know it would be one payment, $10,000. Okay, so you know that you've got to equate these payments. Okay, so you start by saying, I'm going to pay one debt off, or my debt off using one payment, or in other words, this $10,000 here. But first, all of these payments are at different periods in time. So we have to discount them back to a focal date, remember from equivalent values. I'm going to call today the focal point. Okay, so today is obviously time 0. That just means the number that you arrive at the end will be the number of compounding periods starting from time 0. You don't have to do any math after the fact. So that means that we have to find the present value for every one of these 4 payments. All right, so I'm going to change colors here. I'm going to call this payment 1, payment 2, payment 3, the 2,000, 3,000, and 5,000. And then our single payment, I'm going to call it number 4. All right, so if we write this as an equation, we have the present value for our large one-time payment, which was number 4, has to be equal to the present value of the 3 payments you were going to make, right? So if you substitute this in, all right, all I'm going to do here is substitute the present value formula into each one of these. You're going to get $10,000 divided by 1 plus the periodic interest rate to the exponent n4, right? Because that's the amount you're paying then. Has to be equal to payment 1, $2,000 divided by 1 plus the periodic interest rate. And I'm using, again, the subscript n1 here, right, to denote the first one, plus $3,000, which is payment number 2, divided by 1 plus the periodic interest rate to the exponent n2, plus our third payment, $5,000, divided by 1 plus the periodic interest rate, and that's the exponent n3. Okay, so what other information do we know in this equation? Well, we can calculate the number of compounding periods for all three of the payments we would have had to make because they were provided in the question. We can also calculate our periodic interest rate, and we know our number of compounding periods because it was given that it was compounded monthly. So I'm going to just use the right-hand side here, and I'm going to figure out what do we know. Well, we know that our nominal interest rate is 9%, which is 9 divided by 100, removing the percentage sign, which is 0.09. We know our number of compounding periods per year, M, is 12 because it's given as monthly. So our periodic interest rate, I, is J divided by M, which is 0.09 divided by 12, or 0.0075. So now we have all this information, we can calculate the number of compounding periods for the three payments we would have made, right? N1, and again, all these formulas are the number of years multiplied by the number of compounding periods per year. So for N1, it's 6 months, or converting it to years, 6 divided by 12, because there's 12 months in a year, multiplied by 12, right, since the number of compounding periods per year is monthly. The 12s cancel, and you get a value of 6. For N2, that's equal to the number of years multiplied by M again, which is 15. And again, you have to divide it by 12 because it was given as 15 months multiplied by 12. So the 12s cancel, and you get 15. N3 is equal to the number of years multiplied by M, which is 24 divided by 12 because we're given as 24 months multiplied by 12. 12s cancel, and you get an answer of 24. So we can substitute all of these values into this equation. So we have 10,000 divided by 1 plus 0.0075, the exponent n4. We don't know that value, right? That's what we're trying to find. Is equal to 2,000 divided by 1 plus 0.0075, and n1 is 6, plus 3,000 divided by 1 plus 0.0075 to the exponent 15, because that's for our second payment, plus 5,000 divided by 1 plus 0.0075, and that's the exponent 24. So we can multiply each one of these values out. So on the left side, we stay at 10,000 divided by 1 plus 0.0075 to the n4, and that's equal to the first term, $1,912.32, plus the second term, $2,681.92, plus the third term, $4,179.16. So all I did was multiply each one of these out. Okay? I'm going to just switch it to the other slide, and we'll copy over this relevant information before we finish answering this question. So our equation, I'm just going to write it out again. 10,000 divided by 1 plus 0.0075 to the n4. And I'm going to say equals, and I'm just going to add those three numbers up, okay, from the last equation. So the $1,912.32 plus $2,681.92 plus $4,179.16. So that is equal to $8,773.40. So you see, just like last question, now we're at a point where you can see this must be equal to the present value of this $10,000. Okay? So this is a present value formula. That means that your present value for this case is $8,773.40 The future value is the same as it always has been. It's the payment you're going to make in the future. In this case, it was that one-time sum of $10,000. And you know your periodic interest rate is 0.0075. So you can use now the formula we derived to solve directly for this term N4, the only unknown that we don't have. So that value, N4, would have to be equal to the ln of the future value divided by the present value, divided by the ln of 1 plus the periodic interest rate. Substituting our values, that gives a ln of $10,000 divided by $8,773.40, divided by the ln of 1 plus 0.0075. Okay? If you calculate that out, you get a value for n, okay, of 17.5. So what that means is, if we want to figure out the number of years, or when it would have to be made, n is equal to the number of years multiplied by the number of compounding periods per year. So this value that you're given, remember your value for m was monthly, so this is actually 17.5 months. If you want to convert it to years, that would mean that you substitute 17.5 is equal to the number of years multiplied by 12, the number of compounding periods per year, and now you can solve for the number of years. You do that simply by dividing both sides by 12. And if you do that, okay, these 12s cancel, and you're left with your number of years is equal to 1.46. Okay, so you can have it all depends what I ask in the question. I didn't ask you for it to be in a certain amount of days or months or years. So you could have left it as 17.5 months, which is like what I have in the solution. Or you can take it a step further and follow the same steps to get our answer in years, just like we have in the past. All right? So now we're going to change a little bit, and we're going to look at solving for I, the periodic interest rate. So unlike when we solved for n, where we had to look at the ln function, okay, that button on your calculator, now we have to review fractional exponents. Okay, so our basic formula for that was, remember, this term here that I'm called n, that was the order of a root. Okay, so this is an nth order root. Okay, I'll give you a few examples below. And if you had that, you could write it as a, or in other words, the item under the square root sign, raised to the exponent of 1 divided by the order of the root. So the order of the root was placed in the denominator of that exponent. Okay? So let's look at a few examples. First example, 4 to the exponent 1 divided by 2. And that's equal to the root of 4 and then the second order. What that means is that some number multiplied by some number has to equal 4. Okay? The reason that there's 2 is because it's a second order root. So if you do this calculation, you get an answer of 2. And that number makes sense because remember, 2 times 2 is equal to 4. Looking at a second example, all right? Okay? These first two examples are ones that you can kind of think of in your head. The second example is 27 to the exponent 1 divided by 3. Remember, that's equal to 3 times the root of 27. So that means that some number times itself 3 times is equal to 27. The answer to that is 3 times 3 is 9, times 3 is 27. So if you calculate that out, I thought of it in my head and got to the answer of 3 because it was a basic example. But you can place that as well in your calculator. And I use either function. You can either do 27 to the exponent. Remember, it's the little triangle hat symbol. And your exponent would be 1 divided by 3. Or you could use the root function on your calculator to calculate it. I find this way to be much simpler. Okay? So let's look at a next example, okay? 50 to the exponent 1 divided by 4. And that's the same as putting 50, okay? Then pressing that little hat symbol and putting in brackets 1 divided by 4. I always put it in brackets, so then you know, your calculator knows to put that fraction in as one number, all right, in your calculator first. Again, it wants to follow order of operations. And if you calculate this one out, this one you can't do in your head, right? And you get 2.66 for round numbers, I included, with a lot of decimals, okay? So this principle is going to be important when we derive the formula to solve for I, okay? Again, I'm not looking at for you to actually have to do this derivation of a formula, okay? I just want you to understand where I'm coming from when I do these derivations and what rules I'm using, which are rules that you have learned in the past, but just applying them to solve this equation, all right? Just solve for that term I. Because if we start, just like we did last time, with the future value formula, future value is equal to present value times 1 plus the periodic interest rate to the exponent n. So you see, we're trying to solve for I, right? That term is buried in brackets with an exponent, so we've got a lot of items that we need to remove from this right side of the equation. We want it to be I equals something, okay? So you can substitute those values in and obtain your periodic interest rate. And from that interest rate, remember, I is equal to j divided by m, you can then determine what the nominal interest rate would need to be, assuming in the question you know the number of compounding periods per year. So what I'm going to do first, all right, is I'm going to do the easiest step. The first item I'm going to remove is remove present value from the right-hand side of the equation. And to do that, I'm going to divide both sides by PV. Okay, remember what you do to one side of the equation, you have to do to the other side of the equation. So the PVs cancel. And what you're left with, I don't have it written here, is future value over present value is equal to 1 plus I to the exponent n. All right? Now, you need to get rid of that n. You want to remove that n from as an exponent. So what I'm going to do is I'm going to take the n root of both sides. Right? Remember from our formula, you can take the root to a certain letter. So what I'm going to do is I just put the root, okay, I'll draw over it, and I wrote the order as n. Remember, like every other function we've done, adding, subtracting, multiplying, dividing, or in the last example in this lecture, taking the ln, you have to do the same thing to the left side as the right side. So that means I have to take the nth order root of the future value divided by the present value. Okay, now remember, this looks and you're thinking, oh my God, where did this root sign come from? Why is it useful? Well, remember that formula from the last slide, okay? That nth order root of something a is equal to the value that's under the root sign to the exponent of 1 divided by the order of the root, or n. Okay, so that means I can rewrite that equation. So I'm basically taking this equation here and I'm rewriting it using that formula. Okay, so I've taken everything under the root sign, future value divided by present value, and I've raised it to the exponent of 1 divided by n. Okay, on the right hand side, I've actually done the same thing. Okay, so I've taken everything under the root sign, 1 plus I to the exponent n, and then I've taken that to the exponent 1 over n. So basically, this exponent, what that was 1 plus I to the exponent n, that all to the exponent 1 over n. And if you remember having two exponents, an exponent raised to another exponent, it's the same as multiplying those two exponents together. So it's 1 plus I to the n times 1 over n, which is 1 plus I to the n divided by n. So that's the step I took there. Now, just like any other term, okay, we've got the same value in the numerator as the denominator, n and n. So those actually cancel and become 1, right? And you remember, anything to the exponent 1 is just whatever's sitting in here, right? 3 to the exponent 1 is 3. 4 to the exponent 1 is 4, okay? So we can simplify that right-hand side. And what happens is it just becomes 1 plus I, okay? So because of that, now we have 1 plus I on one side, and we have this equation, future value divided by present value to the exponent 1 divided by n on the left-hand side. So now we just have one item left. We have this number 1 on the right-hand side that we need to remove. So to do that, we simply subtract 1 from both sides because you have to do the same thing to one side as you do to the other. So you arrive at having just I on one side of the equation. All I've done is moved everything from the right side to the left side and the left side to the right side. So you have I is equal to the future value divided by the present value, all to the exponent 1 divided by n. Again, n is the number of compounding periods, total number of compounding periods, minus 1. Okay, so that's the formula I want you to remember. Again, I recommend going through how I derive this multiple times. It may be a little confusing on this first time through. I'm trying to apply these concepts to this equation, but I encourage you to watch it multiple times, as well as maybe going through the next few examples to see how much easier it makes problems when you have a straightforward formula now that's just solving directly for I. So let's look at an example. What is the periodic interest rate if $200 accumulated to $318.77 in 8 years with interest compounded annually? All right, so again, we're looking for the periodic interest rate. So I'm going to start with the formula. I is equal to the future value divided by the present value to the exponent 1 over n minus 1. So what do we know in this problem? We know the future value is $318.77. The present value, the amount you started with, is $200. Okay, and we know a couple other terms. N is equal to the number of years multiplied by m. Now, we haven't looked at m, right? But do we know it? Well, it's compounded annually. So if it's compounded annually, m is just 1. Okay? And we know that the number of years provided in the question was 8. So we can solve for n. N is equal to 8 times 1. 8 years times 1 compounding period per year, which gives you 8. So now we have all this information. We can just substitute it directly into this formula and solve directly for I. So you have I is equal to your future value, 318.77, divided by your present value, 200. That's the exponent 1 divided by 8, and that's minus 1. So if you substitute those all in your formula, you get an answer of 0.06. Remember, any time that we were placing interest rates into a formula, we always had to find it as a decimal. But you can go the other way around to find it as a percentage, and you'd simply multiplied by 100%. So that means your periodic interest rate would be 6%. Okay? Let's look at one more example. At what nominal interest rate, compounded quarterly, will $250 double in 10 years? Keyword here, nominal. Okay, that doesn't mean you can't solve for the periodic interest rate first, because you can find the nominal interest rate from that. So I'm going to start with the formula. I is equal to the future value over the present value, the exponent 1 over n minus 1. Okay, we also know that I is equal to the nominal interest rate divided by the number of compounding periods per year. That'll become important when we're solving for the nominal interest rate. So let's look at what we know. Well, it's asking for when $250 will double. So that means our present value is $250, but our future value is double that, which is $250 times 2, which would be $500, right? Because we want to double our money. We also know our number of compounding periods, M, okay? It's given as quarterly, which is 4. We don't know, however, what our nominal interest rate is. Well, the other term we can calculate, though, is N. Okay, I'm just going through the list of each of these terms that we could calculate, right? It's all the same terms that you're just calculating for each time. N is equal to the number of years multiplied by the number of compounding periods per year. So we know from the question it's 10 years, and that's multiplied by 4 compounding periods per year because it's quarterly, which gives you a value of 40. So we can solve for I. So I now is equal to our future value, 500, divided by our present value, 250, to the exponent 1 divided by 40, minus 1. So if you place that into your calculator, you get a periodic interest rate, 0.1748. Remember, that has to be converted to an actual percentage if you want to see it as a percentage, and you can multiply that by 100%, and you get 1.748%. Remember, that's the periodic interest rate, though, and they're asking for the nominal interest rate. So that's why I showed you this second formula, right? Normally, we start with the nominal interest rate and the number of compounding periods per year, and we find the periodic interest rate. Now we're just going to work backwards, okay? So I'm going to look at this formula. I is equal to J divided by M. And we know that I is 1.748%. That's equal to J divided by 4, the number of compounding periods. So now we just need to solve for J. So how do we do that? Right? Well, we've got this 4 in the denominator on the right side, and we need to get rid of it. To do that, we multiply both sides by 4, because then we have 4 divided by 4, which cancels. And we're left with J is equal to 1.748 times 4, which gives us 7%. Okay? So remember, that's a key item to look for in this question. Is it asking you for a periodic interest rate, like the last question did? Or is it asking you for a nominal interest rate? All right? It's just an extra 1 or 2 steps to get from the periodic interest rate to the nominal once you've used this equation that we've derived. Okay? So this is our last example for this. Then I'll just give you a list of some practice problems to do for this lecture, okay? So suppose $1,000 earns interest of $93.81 in 1 year. Part A, what is the nominal, keyword here, interest rate if compounded annually? Part B, what is the, again, nominal interest rate if compounded monthly? Okay, so I'm going to start with our formula. Let's see. Let's start by writing, this is part A. I is equal to our future value divided by our present value. The exponent 1 divided by m minus 1. So what do we know here? We know our present value is $1,000. And we were given the amount of interest we earned in the 1 year period, which means we can take our future value of $1,000 plus the interest we earned, right? $93.81. And if we do, then we get $1,093.81. The other items we know, since it's part A, it's compounded annually, so we know that M is 1, all right? And we were given in the question that for both parts A and B, this was invested for 1 year, all right? So we know that our total number of compounding periods, N, is equal to the number of years multiplied by the number of compounding periods per year, which is simply 1 times 1, which is 1. So we can substitute each of these values in now. I is equal to $1,093.81 divided by 1,000. That's the exponent, simply 1 over 1 minus 1. And we get an answer for I of 0.0938, which again, to convert to a percentage, times 100%, which equals 9.38%. So we can convert this to a nominal interest rate. In this case, because it's annually, the periodic interest rate and the nominal interest rate are the same, right? Because our value of n is just 1 times 1. Okay, so that means that this is actually equal to j, which is our nominal interest rate. Contrasting that, on part B, I'm going to start with the same formula. The future value over the present value to the 1 over n minus 1. The values here are still the same for present value and future value. Present value is $1,000. Future value is $1,093.81. Our number of compounding periods per year is 12, not 1, so it's different. And our total number of compounding periods, n, which is the number of years multiplied by our number of compounding periods per year, is equal to 1 year times 12, or it's equal to 12. So now we can substitute these values in, right? So we get I is equal to $1,093.81 divided by 1,000. So the exponent 1 divided by 12, and that is minus 1. So if you substitute those into your calculator and solve, you get a value for I of 0.0075, or you might get 7.5 times 10 to the negative 3. Those are the same term, okay? It's the same value. Remember, the negative 3 means you would actually just move this 3 decimal places to the left and substitute zeros. So that's how you would obtain 0.0075. Now in this case, we need to convert to a nominal interest rate. It's not annually. It means it's compounded more than once. So this periodic interest rate actually isn't the overall interest rate for the year. So remember, I is equal to j divided by m. Okay, so j is the nominal interest rate. Substituting these values in, we get 0.0075 equals j divided by 12. Okay, so to solve for this, we've got a 12 in the denominator, so it means we have to multiply both sides by 12 in order to remove it. So that means on the right side, we have 12 divided by 12, which cancels, so we have just j. And if you multiply this out, you get j is equal to 0.09, which you can convert to a percent. Okay, I converted this question to a percent at the very end. You can do it at the start or at the end, provided you make sure you show the percentage sign in the equation. Okay, otherwise you don't know whether that number is a percentage or not. And if you calculate that out, you get a value for j of 9%. So your nominal interest rate here is 9%. And that makes sense that it's different and it's lower, right? And the reason for that is because it's compounded more often. Okay, so if it's compounded more often, 9% interest compounded monthly will make you as much money as 9.38% interest compounded annually. You'll see in our next lecture, we're going to talk about effective and equivalent interest rates, and you'll kind of get a better sense as to why that is the case. Okay, so that was all I had for this lecture. These are your practice problems that I'm recommending, all the odd numbered problems from your textbook for both exercises 10.1 and 10.2. 10.1 is for finding the values of n, and 10.2 is for finding the values of I. I always pick the odd numbered problems because they have solutions in the back of your textbook. As per every other lecture, if you have questions, send me an email or we'll talk in our tutorial this week. Thanks.